Alright, so we did an exercise before this where we're dealing with how do we find the derivative of standard functions that you can find using addition, multiplication, projections, composition, etc. But this time, now we're adding in integrals. And so let's see, we'll start with part A. And note that if we're going to let s of x be the integral from a to x of the function g, then by the fundamental theorem of calculus, s prime of x is g of x. Now, how do we know this? We don't. This is another instance where we have an exercise in this textbook that relies on prior knowledge that you learned in calculus, but which we haven't been introduced to yet rigorously in this textbook. Therefore, we sort of have to take all these things as assumptions and not as facts that we previously learned. Like the fact that if you define s of x to be the integral from a to x of g, then s prime of x is equal to g of x. You can prove this, and this is true, but we haven't proved it yet. So, that's a little annoying, but it's not really that big of a deal. It's more of a thing that I find annoying, and as a mathematician you find annoying, because mathematicians hate assuming things that you can prove. Because what you should do is you should prove it and then use it, instead of assuming that it's true and then using it. But anyways, okay, so we've got f of xy is the integral from a to x plus y of g. So we've got f of xy is just s of x plus y. So if we want to take f prime of xy, then we have to use the chain rule. So it's going to be s prime at x plus y. Oh, wait. Before we get there, we have to do the thing where we turn everything into projections because we don't know what a partial derivative is yet. So f of xy is s of pi 1 of xy plus pi 2 of xy. So if we want to take f prime of xy, this is going to be, we have s prime of pi 1 plus pi 2 times the derivative of pi 1 plus pi 2. So s prime of pi 1 plus pi 2 is just g of pi 1 plus pi 2. So it's going to be g of x plus y. And then here when we take the derivative of pi 1 plus pi 2, we're just going to get the vector 1, 1. And so this is the vector that we end up with. And indeed this is a, let's see, f is a function from R2 to R. So our derivative needs to be a function from R2 to R. So as a matrix it needs to be a 1 by 2 matrix, and that's exactly what this is. We've got one row and two columns. And there we go. Okay, so B is going to be similar. We've got f of xy equals s of xy, which is s of pi 1 times pi 2. And so f prime is going to be s prime of pi 1 pi 2 times pi 1 pi 2 prime. So this is s prime is g, and so this is going to be g of xy times pi 1 prime pi 2 plus pi 2 prime pi 1. So this is going to be, here, I'll just go on the next line because we're going to need to use the next line anyways. So this is g of xy. Now we've got 1, 0 times y plus 0, 1 times x. So this is g of xy times the vector yx. And there we go. And then finally, we have this thing, which is annoying. So what we're going to do is we're going to observe that f of x, y, z, so it's the integral from x to the y to this thing involving sines of g. But given a, we can write this as the integral from a to sine of x. I'll just write that because it's supposed to be sine of x sine of y sine z, but I don't want to write all that out, so I'm just going to write this. So we take the integral from a to this thing of g minus the integral from a to x, y. The integral from a to x to the y of g. And why is this? This is because the integral from given points a and b and c, where you've got a less than b and c is between a and b, then the integral from a to b is equal to the integral from a to c plus the integral from c to b. So the integral from x to the y to sine whatever is going to be the integral of x to the y to a plus the integral from a to sine whatever. And then what you use is you have this integral from x to the y to a, and then you can flip the order of the integral. So instead of going from x to the y to a, you can integrate from a to x to the y, and when you make that switch, you change the sign of the integral. So that's why we have a minus sign here. So these facts that I've used about integrals, being able to break them up and then flip them and change the sign, these are things, again, we haven't proven these, but we know them from calculus, so we're just going to use them here. But anyways, this is nice because now we have s of sine of whatever minus s of x to the y. And so now we can actually take the derivative, because f prime is going to be, we have s prime of, and here I'll write out, sine of x sine of y sine z. And then we have to multiply by the derivative of this thing, y sine z, minus s prime of x to the y times x to the y prime. And so now we have to go through and be like, oh, what are these things? But actually we don't, because we already have done these in the previous exercise. So go back to that, because I don't want to do them again, because they're really annoying, particularly this first one. Now we have to multiply by, and this one is just very obnoxious. Cosine of x sine of y sine z times this vector, which I'm not going to fit on this line. So the vector is sine of y sine z x cosine of y sine z times sine z, and then x cosine of y sine z times y cosine z. Okay, so that's the first term. Second term is, so we're subtracting, again we've got the g times x to the y, and then we're multiplying by this vector that we computed in the last exercise. We've got x, or y times x to the y minus 1, x to the y natural log of x, and 0. And so there we go. So this is useful because this, not only is it a good way for us to practice differentiation, but it also shows us how to take derivatives where the function is actually in one of the bounds of the integral. And in fact, I remember last year I was in a finite element method class and we were proving something about, we were talking about solutions to, like, maybe it was Berger's equation or something. But we were talking about certain solutions to partial differential equations, and particularly solutions that have discontinuities. And there was one part where we had to actually do an integral where we had the integral that we were doing had a function in one of the bounds of the integral. And I was like, wait, how do we do those again? But then I was like, oh yeah, you have to consider the integral as a function and use that thinking to do the chain rule. So this is not a common technique. This doesn't come up all the time, but it is something that comes up, and you need to know what to do when that comes up. And so what you do is this. And so this is really useful as an exercise, because this is something that if you continue to go on in mathematics, you will come across again. And it might be a thing where you forget how to do it when you see it. But hopefully after seeing this exercise, you either will know how to do it so you won't forget, or you'll know where to go to get the information on how to do it. So, whatever the case, we've done what the exercise asks, and that's it.